talking about non-regular languages, and there was just one example left over at the end that we didn't quite get a chance to discuss, and that is this. X bar means not. This was that last example. And the idea is to prove that this language is not regular. I hope you remember how we did these. There's several on the homework like this too. You take a derivatives in some way and show that you're going to get infinitely many possible answers. Did anybody do this one? Even if you don't remember, you might have it written down. What did you take for the derivatives?
Oh, I didn't do it.
Oh, okay. Stretching his hand out. Anybody manage to work this out? I usually say something like let di equal. I'll call this L.
Is that x equals 0 I y? It's the third one, right?
Yeah, so take the derivative with respect to 0 to the I. This looks very strange, but remember the alphabet symbols in this language are zeros and ones. So when you take the derivative, it's either with respect to 0 or respect to 1. Don't ever do this in calculus. There is no such thing as derivative with respect to 1 or 0 in calculus. But yeah, this is how you should do it. Now, what's weird about this example is that these strings don't all begin with zeros. The question?
Yeah, I was thinking, do you need to do 0? Could you also use 1?
You could use 1. Yeah, that's totally the same. But I mean, we might as well do 0 here. But yeah, you could do it with 1 and it would work. You'd have to rewrite everything slightly differently from what I'm about to say. But the idea is these strings do not all begin with zeros, but some of them do. So, and this is what he said before, you can think of x as beginning with 0 to the I followed by something else. All right? And then when you take the derivative of that, you're going to cancel the 0 to the I off the front of it. But the question is, what does the rest of it look like? So if x equals 0 to the IY, then x followed by x bar equals 0 to the I, y. And then what does x bar look like?
1 to the I.
Yeah, that would look like 1 to the I followed by y. Y bar. Yeah, someone was giving me the universal hand signal for bar. Yeah. So it looks like this, right? X bar, remember the bar means not, so it's going to turn all of these, which used to be zeros, will turn into ones, and then everything else will just turn into whatever it turns into. So that's why the y turns into a y bar. Okay, great. And now we can say what the derivative will look like. It will look like all of these things, but you just cancel 0 to the I off the front. So it looks like y followed by 1 to the I followed by y bar, where this y now can be any string in 0, 1 star. And then you have to just write some words explaining why these sets are all different. And they are all different because di, so this is di, right? This has I ones in the middle, right? Di is the one which has I ones in the middle. Like for instance, D1 has 1 in the middle. D2 has 2 1s in the middle, etc. Those are all going to be different sets. So this has I ones in the middle. So these are all different. And remember, the theorem was if you have infinitely many different derivatives, then the language is non-regular. All right. That's how we do it. Any questions about that? Like I said, there are some homework problems similar to this one. All right. Excellent. Actually, I wanted to do, this was just left over from last time, but for today I want to start off something completely different. We've said everything that we need to say about derivatives and showing that this or that language is not regular. We're going to move on to something else. And unfortunately, I don't know if this is unfortunate or fortunate, The next thing that we're going to talk about is another thing that some of y'all computer science majors may have seen in one of your other classes. I know, unfortunately, the CS majors take this class and often in the very same semester also take another class where you talk about regular expressions and state machines and such. This is one more thing that they also talk about in that other class, and it is grammars. We're going to talk about grammars, grandmas, as they say. Grammars is another way to kind of build a language, which, vaguely similar to regular expressions in that writing down a grammar is some sort of like encoded way of describing how to build strings in your language. So I'm going to say this is another general way to specify a language. I think, I hope that when I talk about things that are the same as in this other class, I hope that it's a different enough perspective that it's not just like the same exact stuff 2 times. Another way to specify languages. I've thought about trying to coordinate with them and like eliminate all the overlap, but a lot of the people who take this class are not computer science majors, and then there's no overlap for them. And then I have to do all that stuff for them, but it's not obvious how to proceed. Anyway, any grammar defines a language, and actually grammars can define languages that are not regular. So grammars are more capable than regular expressions, I will say. More complex than regular expressions. A regular expression can only generate a regular language, but actually you can make a grammar for even some languages which are not regular. All right. For example, I'll say e.g. This language, A to the N, B to the N, which is everybody's favorite example of a non-regular, this has a grammar. And it's not really very hard to do with a grammar. So we'll talk in detail about how to make a grammar for languages like that. But anyway, I'll try to describe sort of the basic idea behind grammars and why it's called a grammar. Let's say, let's make a grammar for English sentences. I'm talking about real language here. Sentences like, something like, very simple sentences like, I love mom, or you want candy, or we see candy, right? This very simple English sentences. A grammar for this. The idea is you try and analyze these in terms of like grammatical structure. These are all subject, verb, object, right? That's what the linguists call this kind of a sentence. Subject, verb, object, which is the typical order in which you build a sentence in English. Other languages, you build the sentence in other orders, but this is how we do it for the most part in English. Subject, verb, object. And the way that you can write this, actually, rather than S there, would you mind if I use a N for noun? Just because in grammars we use the letter S to mean something special. So I'll say this is noun, verb, object. All right. Anyway, here's how we would write this as a grammar. It would look like, so S is where you start in the grammar. And every grammar we ever do, we're always going to start with S. And then it says S, and then this arrow, and then NVO, and then the arrows, you think of them as like substitutions. Oops. So what the first line says is S when we start. The S can turn into a N, a V, a O. And then the next line says the N can become I, or you, or we. That vertical bar, the pipe there, means like or. This means or in a grammar, all right? And the arrow indicates a legal kind of substitution. If you start with S, you can change that into NVO. If you see an N, you can change it into one of those three things. If you see a V, at least in the example sentences up there, the verb could be love or want or see. And then the O could be the only objects I care about, mom or candy. All right? This is a grammar which specifies that very simple form of sentences. All right? And any of those sentences up there can be derived using this grammar. So this is the terminology that we're going to use. Each of those arrows is called a production. A production, because we imagine these as somehow rules which are used to construct a sentence, or rules which we use to produce a result. So those are called the productions. And the way to indicate sort of how you produce a final answer, we can write out what are called derivations, like now in our book they use different arrows for different things, but for instance, a derivation of the string I love mom would look like S becomes NVO, and then that N becomes a I, and then I have VO, and then the V becomes a love, so I have I love O, and then the O becomes a mom. I love mom. All right? That is called a derivation. And in our book, they use the sort of doubly arrow there. The single arrow is used only when you're writing down what the grammar is. Those are all the individual productions. This double arrow is how you write down a partial substitution. So this double arrow, I had IVO, and I turned it into I love O. So this double arrow indicates substituting a little piece of this according to one of the productions from the grammar. All right? Not too complicated, I don't think. We can make a slightly fancier version of this same grammar. So here's a fancier one. How about this? S goes to, I'm going to do NVO or NV, I'll put a M there. So the N and the V and the O are going to be the same as before. Let's say the M is I, U, V. The V is love or want. The O is mom or candy. And let's say the M, this is my new one, is either the or my. All right? So this allows you to, if you want to, you can insert an extra little word in there. So rather than just saying I love mom, if you want to, you could say instead I love my mom, or I love the mom. Right? That's what this M allows you to do. So I'll just say now we can derive something like I see. I forgot see. That was another one of my verbs. I see my mom. Right? That is allowed with this grammar, which was not possible in the previous grammar. All right. So this is the idea of grammar. Like the concept arose from trying to study real life grammar in spoken human languages and analyzing the parts of grammatical parts of speech and sort of in what ways you're allowed to combine parts of speech together. All right. Human languages, you might wonder if you could actually write a real grammar that specifies, say, the rules for the English language. Could you actually construct a grammar in this way, which which accurately represents the rules of the English language. I think linguists have differing views on this point. I think most linguistic types would say that's not actually possible because human beings, our grammar that we use does have specific rules, but also people are always flexible with the rules in various ways, and it's not really possible to do this. But programming languages, for the most part, do have very specific rules, and you can write the grammar, for instance, for Java can be written down like this, or for Python or something like that. Anyway, let's talk. So in our case, we are usually not going to be doing these things about I love my mom or whatever. We usually are going to look at grammars that look like, I'll just say, we'll usually do ones like this. How about S goes to AS or X, X goes to BX or epsilon. All right, that's a grammar for creating strings of like A's and B's. All right. And we want to know, the obvious question would be like, what are the different types of strings which you can create using these grammar rules out of just A's and B's? So, for example, well, let me just say, we always start with the S. And do substitutions using, those arrows, right? For example, here we can derive A, B, B. Now, it's not immediately obvious looking at the grammar that that's even possible, but I'm telling you, it is possible. How do we do it? We start with S. Remember, when I write a derivation, I use the double arrow. When I'm just writing what the original rules are, I use the single arrow. This is the way they do it in our book. Now, you will learn, once you get more comfortable with grammars, you'll be able to look at various pieces of this and kind of make intuitive judgment calls about what the various pieces do. But when I see this S goes to AS, that is kind of like something which I can use to sort of do a loop and create a bunch of A's. So I'm going to do that one first. I'm going to do S goes to AS first. And then, remember what I'm looking for? I'm trying to derive this, AAABB. I begin by creating an A. I'm going to do that same one again. S goes to AS. Now it will say AAS, right? Because I substituted the S with an AS, and there was already an A in front of it. And then I'm going to do that one more, because I want to see the string I'm aiming to get has 3 A's at the beginning. So I'm going to do that same one more time. AAAS. All right. What should I do next?
UAAX.
Yeah, I should go S goes to X. You don't want to do this other one again because you're going to get another A, and I don't want another A. So I'm going to make S go to X first. So it's going to say now AAAX. And now you see this, X goes to BX. You can do this over and over again to create B's. And I want to do it twice because I see 2 B's there. So I go AAABX. That was one time. Another time, AAABBX. All right. And finally, X goes to the empty string. Right? That's what this, this empty string. It means the empty string as always. So this can become AAABB empty string, which is equal to AAABB, which is what I wanted to get to in the end. Yes?
Yeah, that's what I was going to ask. Like, if when we get to the end, like the empty, do we need to write the empty? Like, do we need
No, it's fine. Yeah, I mean, if you didn't write this and you just wrote that, that's fine with me.
Okay.
Yeah. And I mean, in practice, once you are used to doing this, you can probably more or less see how this would go entirely in your head. But if I actually asked you to write down the derivation, this is what you'd write down. I don't care if you write this step there in the middle there. All right? The set, so you can look at a grammar like this and ask yourself, what are all the possible strings that I could derive using this grammar that has a name? The set of all strings derivable using the grammar is called the language generated by the grammar. Just like, NFAs or DFAs, it generates a grammar. So it's called the language generated by, if this grammar is called G, maybe I call this one G, right? That's called a grammar. If you give it a name G, then the set of all strings derivable using this grammar is called the language generated by G. And we write this, no surprise, like this, L of G. It means the language generated by G, the grammar G. All right? This is just simple notations. For example, here's another example of a grammar. This one only has sort of one line. S goes to A, S, B, or epsilon. What is the language generated by G? Well, maybe we can just sort of practice a few derivations, right? Some derivations. I could begin with S, maybe do this ASB once, and then turn the S into an empty string, and I'd get A empty string B, which is AB. So that's one thing that you can make using this grammar. What else could you make? Well, you could do that ASB thing more than once, right? I just did it once, but you could do it twice. What do you get if you do it twice? Then it looks like ASB first, and then again AASBB. And then make the S into the empty string, and you'll get AABB, right? That's what happened when I did it twice. What if I do it 3 times? Can you see what's happening here? It'd be AASBB, and then do it once more time. I get AAASBBB, which is AAABBB. Right? In this case, L of G, can anybody say what it is as a set? Yeah?
A to the n, B to the n.
Yeah, this is A to the n, B to the n. Our favorite example of a non-regular language. So, I hope you're convinced now, grammars can create non-regular languages, and it's not even that hard, right? As far as grammars go, that's a pretty simple example. And it generates a non-regular language. All right? Excellent. We can get even fancier with the grammars. So one thing that I haven't done in any of these examples so far, but it is legal, although, if I'm honest, we're not actually going to do this very often, but here's something fancier you can do in a grammar. S, let's say S goes to ASB, or epsilon, and AS goes to SA. How you like that? This is also a legal grammar. So the first line is just like the one that we just did. It can, by itself, the first line will generate A to the n, B to the n. The second line says, whenever you see AS, if you want to, you can turn that into SA. All right? What difference does that make? Actually, it makes a difference. You can create other kinds of strings here. So in this grammar, I'll say now we can get A to the n, B to the n by just not using the second line. You can make anything that looks like A to the n, B to the n. But also, you can get some other stuff that you couldn't get before. Can anyone think of an example of a string that you can get now that by using the second line, you can get some things that were not allowed before? I think you can do A, B, A, B. Check it out. Let's try it. So I have to start with AS. S goes to ASB, just otherwise you won't get anywhere. The only other alternative would be to go to epsilon. Okay? Can anybody see from here? How do you get to AB, AB? What should I do next? Yeah?
AS goes to SA.
Yeah, so I'm going to do that other weird rule. AS goes to SA, so this becomes SAB.
S goes to ASB.
Right, and now I can create a new ASB, and then there's an AB at the end. And then S goes to empty string, and we're done. So we get AB, AB. All right? Yeah, it works. Yes.
So on the left side of the productions there, you can't have like multiple.
Yeah, so we need to have a little frank discussion about what exactly is allowed in this case. The first part of the answer is on the right side, you can have whatever you want. So of these productions here, you can put anything you want on the right-hand side. On the left-hand side, there are some rules, and the rule is that, we need some more terminology, and then I'll say the rule very clearly. But can I just say, before I say that, about this particular example, it's natural to ask what are the possible strings you can get from this example, and I'm just going to say, in this case, L of G is hard to describe. Strings in this language must have the same number of A's and B's, because you can see in the grammar, the only step which actually creates new letters is this one, right? The only time when you can create a new A or a new B is by doing that step. And that step always creates an A at the same time that it creates a B. So that means as you go, you're always going to have the same number of A's and B's. But the order can be moved around in a weird way by using this step. And I would say it's hard to describe exactly what you get from the end. You can't actually achieve any possible ordering of A's and B's. For instance, it's not possible to make just BA with this grammar. So it's complicated. And you know, sometimes grammars are very complicated to say what the language is, especially if you have weird business on the left side of the arrows. That makes it especially hard to analyze. All right. Well, let's talk about some terminology. I hope that this is all fairly, straightforward so far. So basic terminology here. We have the ordinary alphabet letters, which are like the A's and B's. Usually we use A and B. So the alphabet letters, by which I mean, A, B, etc. These are called, in the context of grammars, these are called terminal symbols. Terminal symbols. The word terminal refers to the fact that they are what you end up with at the end, right? At the end of one of these derivations, you have just A's and B's. So terminal referring to the fact that they are what you get at the end. And for instance, the big S is not meant to go at the end. If you still have a big S, that means you're not done yet, right? The big S is only allowed sort of not on the end, right? It's not allowed on the end. Those are called the non-terminal symbols. So the others, which we typically, in this class, I'm always going to use capital letters for the other ones. So usually they're like S, maybe X, Y, sometimes like T, whatever, right? Just for convenience, the convention is the terminal symbols, we're going to use lowercase. The non-terminal symbols are going to be uppercase. So these are called non-terminal symbols. Non-terminal symbols, all right? And I might as well tell you right away, we can write down a formal description of what a grammar is. We did this with NFAs and DFAs, remember? Usually when you see an NFA or a DFA, when you encounter one in your own personal life, at the club or whatever, you see the diagram. But the diagram is not the true essence of the DFA. The actual essence of the DFA is that weird tuple thing. And we have a similar description for the grammar. So I want to talk about a formal description of a grammar. Although this, for grammars, the difference between the formal and the informal is not so obvious. I mean, it's not such a big difference as it is for NFAs and DFAs. But a grammar is, so this is the true definition of a grammar. A grammar is it turns out for a grammar there are only 4 ingredients. So it's a 4 tuple. G equals, and the way we write this is V, sigma, S, and P. And I'd have to tell you what the 4 parts are. Where, you can probably guess the sigma is the alphabet of terminals. That is the little a, the little b. The V is another alphabet of non-terminals. The S, the X, the T, whatever, the other, the big letters, right? We really have 2 separate alphabets. There's the terminal alphabet and the non-terminal alphabet. So I'm going to say V is a non-empty set of non-terminal symbols. It includes S, but also maybe some others, although it could be just S. Sigma is a non-empty set of terminal symbols. The A's and B's, or whatever else. All right. S is just one of the non-terminals, and it's the starting symbol. That's what the S is called. So I'm just going to write S is an element of V, right? It is a specific one of those non-terminal symbols. This is called the starting symbol. And P is what there's only one more thing that we need to describe to specify the grammar. I haven't said anything yet about like the arrows. That's what the P is. So P, you could describe this, in an NFA, DFA, we describe this using functions, but and you could do that for grammars, but in our book they describe it using just a set. So P is a set of productions. And each one looks like X with the arrow and a Y, something like that. And here is where I'm going to tell you, he left. He's going to miss it. I'm answering his question from like 10 minutes ago. What exactly is allowed on the 2 sides of the arrow for the productions? Here's what I'm going to tell you. You can all tell him later he missed it. What exactly is allowed here? Each looks like X and then the arrow, and then the Y, where X and Y, you're back just in time. I'm telling them what is allowed on either side of the productions. All right, every production has to look like X, arrow, Y, where X and Y are strings on V union sigma. That means the X and the Y, the things on the 2 sides, they can have some mixtures of the terminals and the non-terminals, right? We've seen that already in our grammars. The things on the 2 sides are allowed to be some kind of mixture of terminals and non-terminals. I'll say, and X what? I wrote this wrong on my paper. X uses at least one non-terminal. That's the restriction. So what this means is the left-hand side of each production, it has to have at least one non-terminal. So what that means is something like, AS goes to B, this is allowed. But something like A goes to BA, this is not allowed. All right, and we disallow this just because if you're going to write that, then A is no longer really terminal. The whole idea, the reason we call A is terminal is because A by itself cannot turn into something else. And this rule would suggest that A can actually become something else all by itself, and we don't want to allow that. All right, so I will X that one out. You never see something like that. All right, this is the formal description of what a grammar is. So, and it's very easy to go back and forth between the formal, a formal description of the grammar and informally. So, for example, here is a grammar just sort of written informally. Something like this. This is an example that we talked about a moment ago. S goes to AS or X, and X goes to BX or epsilon. So to write this formally, it would say G equals, and then a tuple of 4 things. The first thing is the alphabet of non-terminals. Anyone say what that is? It's a set of all the non-terminals. S and X, right. All right, that's the first thing. The next thing is sigma, the alphabet of terminals, which apparently is AB in this example. Next is the specific identity of the starting symbol. Yes, have a question?
Would you have to include epsilon in the sigma or no?
No. So just like for NFAs and DFAs, epsilon does not count as part of the alphabet. I mean, you see it here, but really this is just a notation for the absence of any letter. So it itself doesn't count as a letter. Yeah, thanks for that. Yeah, next will be just S. That is what we're calling the starting symbol in this problem is S. And then finally, the productions. And here, you just write the set of every production one at a time. And so the productions that I'm probably going to run out of room here, but when you write these productions in the formal description, they just have a single string goes to another single string. In the formal description, I was not allowing for the bar, which means or. So the way you write this formally has to look something like S goes to AS, comma, S goes to X. You basically, wherever you see these ors, you just split this apart into 2 separate productions. So this one, which said S goes to AS or X, we have to write that formally as S goes to AS or S goes to X. And then there's 2 more. X goes to BX, and X goes to empty string. Sorry, I had to go to the next line. But it's like that, right? All of this is part of a tuple. Yeah?
So for the production rules, can you have like a non-terminal and a terminal? Can you do SA on the left side?
Yes?
Okay. And then also,
Yeah, like this. This is allowed.
And then you could do like SA too on the left side.
Sure. Yeah. Anything over here which involves any mixture of terminals and non-terminals, although it has to have at least one non-terminal in it.
Okay.
Yep.
And then for the formal definition where you do this set of all the productions,
Yeah.
could we do the same thing like we did for DFAs and NFAs where we substitute a symbol?
Yeah, sure. If you want, you could put a P here and then down here say where P equals whatever. Is that what you meant? Yeah, that's fine. That probably would have been clearer when I did it, just so that I didn't have to go over to the next line. Yeah. Great. Let's say a little something. Just a few more bits of notation. Yes, let's talk about formally. When I write this double arrow, this is part of a derivation, right? X can become Y. What does this mean? This means that we can obtain Y by doing a single production on some piece of X, right? It means, x might be some big string, but when I say x and then that arrow to y, this is a derivation. X, sometimes we say x derives y. It means that you took a little piece of x and substituted it using one of the productions, and what you ended up with was y. There's another notation. We're going to write x arrow star y. The star, as always in this class, means it indicates some kind of repetition or some kind of iteration. So this means we write this when we can obtain y from x after several derivations steps. All right, so when I write the arrow without the star, it means just doing one step you can get from x to y. When I write the arrow with the star, it means you can, perhaps doing many steps, start with x and end up with y, right? And now this is enough notations to define formally what this means, the language. The language of G is, we can write this as a set. It's all x in the terminal alphabet, such that, anybody think you can say what this is using these notations here? In fancy terminology. The language, in ordinary words, it's all the strings that you can get, starting from the start state and doing the productions, all the strings you could possibly end up with. So here I say it's all strings composed of terminals, such that, anyone think you can say something? You want to say in symbols, whatever you can get starting from the starting string, doing the substitutions. We got 1 minute on the clock. Yeah?
Something like S and the arrow, the star, Y.
Yeah, I like this. The arrow, the star. And then what'd you say?
Well, I guess it would be this set. Then the P.
I'm not going to do the P. Actually, I'm just going to do this. So what this means, it's all x such that it is possible to derive x starting from s. That's what this means, all right? And that's what you want, right? It's all the strings for which it is possible to derive that string starting from s. So this means, all strings x such that we can start with s and derive x, right? So this is all of the possible strings which are derivable starting from s. That's exactly what we want, right? It's very simple, simple looking, I guess, way of writing the language of the grammar. All right. I think our time's about up. What I want to talk about next time is how does this relate to NFAs and DFAs and regular expressions? Can you convert one way to the other? That kind of a thing is what we're going to talk about. All right. See you then.